So over the last few weeks, I was working on a project which I kind of begged my physics teacher to work on. And that was a project where I can apply all of this knowledge into one singular product I could show off. And to be quite frank, it is a piece of garbage. When I say that this is a piece of garbage, I mean it's pieces of garbage. Let's start off with the bearings. The front bearing is made from a Cetaphil bottle's shaft when you pop it out. So the shaft of that mechanism is used right here. And most of the chassis is made from kebab skewers. And in the back, I used a paper just a A4 paper. And what I did was I cut pieces of it and rolled it into small little bearing type things to function as a bearing for the back wheels. And when I was younger, I took apart an RC car, and when I put it back together, it didn't work. So I used the front wheels from that alongside with the motor, which is used in this car. That's from an RC car, which was brought in the market. And then in grade 7, I tried to build my own remote controlled car. So I brought gears and wheels. It never succeeded because I didn't know a lot of physics. And then similarly in grade 9, I tried to build a drone, which also couldn't fly because I did not know a lot of physics. And from that drone, I got this aircraft transmitter and aircraft receiver. And this is how this entire car is a piece of garbage. But let's look at the physics which makes this reused car function like the way it does. Alright, let's start off with some momentum and impulse. So we know that momentum is P equals mv, and that is why the mass is limited in this car. As you can see, those kebab skewers and cardboard do not have a lot of mass, whereas I could have used steel, which would have a lot of mass, meaning the car would have a lot of momentum when it's going at a certain speed. Something which is derived from that equation is delta P equals force times delta T, which is the change of momentum equals force times the change of time. And if you rearrange that equation, you will quickly notice that force is inversely proportional to delta T. Essentially, you want to maximize delta T to minimize the force on a vehicle. And this is useful in the crumple zone. Now, we all know that in the 4U curriculum that F equals Kx. And the K value is determined by the kind of compressibility of that spring. But in third year university, you learn what we call Young's modulus, which is stress over strain. Stress is defined by force divided by area, or force over area. And stress and strain is defined by change in that specific material's length over the initial length of that material. And when you rearrange this equation, you get delta L equals F times the initial length times the elastic modulus. And elastic modulus is like a K value, but every specific material has a specific E value, and wood has a specific E value. But putting the math aside, it's fairly obvious that as force increases, longer length is needed. Or if you rearrange this equation to minimize the force exerted, or you will need to maximize the length. And that is exactly what I did here. As you can see, all the expensive electronics such as a battery and receiver and electronic speed controller have been placed at the very back. And in the front, the wheels protrude, and so do those two little kebab skewers, because if a force were to hit, they would crumple and fracture according to this graph. Depending on the force on this object, the material will first obey Hooke's law, it will stay in the elastic region, and then it will have a permanent deformation, and then eventually the kebab skewers and things in the car will fracture. So that is how I incorporated what we learned in the momentum or collisions unit. Let's talk more about the gears used in this car. Gears are used to maximize mechanical advantage. And force from the motor is conserved no matter how these gears are set up. And for mechanical advantage, engineers often use gears to either maximize RPM or torque. RPM is simply just rotations per minute. So say if this little gear rotates once per minute, it would have an RPM of 1. And torque is a twisting force. Let's look at the setup in this car. So gear A is the driving gear and gear B is the driven gear. The driving gear is attached to the motor, where the driven gear is attached to the wheels. Every time this motor goes clockwise, the driven gear goes anti-clockwise, which explains why the motor actually goes anti-clockwise so the car could move forward. Now let's talk about some fun facts about the measurements of each of these gears. The driving gear has a diameter of 1 centimeter and has 12 teeth, whereas the driven gear has a diameter of 4 centimeters and 36 teeth. If you notice, all you have to do to calculate how the forces change in your gear system is divide the number of teeth in your driving gear divided by the number of teeth in your driven gear. Or if you have information for the diameter, just divide the diameter of the driving gear by the driven gear. For our system, we get 0.25, meaning for every one rotation the small gear does, the big gear goes 0.25 in any direction. Say if it was clockwise, it would go anti-clockwise 0.25. It was clockwise, it would go 0.25 the other way. And what that tells us is that the RPM is essentially divided by 4. And the torque is increased by a factor of 4. This gives our car enough twisting power to outdo the static coefficient of friction and set this car into motion. Speaking of friction, let's talk about how I used friction in the wheel specifically to make sure that this car does not go out of control when it's taking fast turns. Friction is equal to the coefficient of friction times the normal force. Now, as you can see that the back wheels and the front wheels both have rubber threadings, and rubber has a high coefficient of friction. And that means that this is maximized through all my ability, but there's something else. There is normal force. In this free body diagram of the car taking a turn like this way, we can tell that Fc is equal to force of friction, assuming that it's not an embankment, and that the force of gravity is equal to the normal force. Now, if you recall the equation for circular motion, it is mv squared over r. And whereas the force of friction is normal force, Fn, times mu s of the wheels. So the static friction of the wheels when it's taking a turn. And that's how you make sure it doesn't drift out of control. And Fn is equal to Fg, which is equal to mass times gravity. Here is where the trick of center of gravity comes into play. I did not want to needlessly maximize mass because that would make the car more susceptible to going out of control because Fc would be bigger. But instead, with all the mass I had, I made sure that it's placed on top of the back wheels. So when the front wheels spin, the back wheels do not spin out of control. And that is the knowledge I've used to design the car in a fashion that most of the weight in this model, and also the last one that is seen in the videos, is all centered toward the back. So the normal force on the back wheels could be maximized, and the car has been built very lightweight, so it could have a minimal mass when it's going on a turn. And that is how I designed the car not to lose control in high speeds. Furthermore, we can tell that the high coefficient of friction is very useful as the motor has instant torque, and when it transfers its energy through the gear system to the wheels, it does not slide, it just goes. And that is because of the high coefficient of friction caused by the rubber threads. Let's talk about radio control. Radio controls are part of the electromagnetic spectrum. And the electromagnetic spectrum is caused by oscillating currents, or alternating current, which creates oscillating electromagnetic fields. Now there's a few types of these electromagnetic fields. First of all, we have the largest wavelength one, which is your radio waves. And they vary from anywhere 10 to the 4 meters to 1 meter. Pay special attention to those because that's what I've used in my transmitter and receiver system. And then we have microwaves, infrared waves, visible light, which you can see, UV, and X-rays and gamma rays. But we only need to worry about radio waves. Fun fact, they have the longest wavelength, and the sign for wavelength is lambda, yet the lowest frequency. And I use radio waves in my receiver and transmitter. Essentially what's happening behind the scenes is that the transmitter, which is the remote, is creating somewhere around 2.4 gigahertz frequency, and then that is transferred through the air, and then that is interpreted as 2.4 gigahertz, and that needs to be the same frequency. That is important because when I was making my drone back in grade 9, I actually shorted a receiver. So when I was looking to get a new receiver, I needed this physics knowledge over here to buy the correct one, which is compatible with my transmitter. But what specific lambda am I most likely to have in this system? As you can see, it could be anywhere from 1,000 meter to 1 meter. Well, let's talk about the different types of waves associated with radio waves, since they have such a large range, as you saw. Say if I wanted to transfer a message from Vancouver, BC to United Kingdom, I would have to use long waves, and these are going to be traveling across the curvature of the Earth. And these are safe to assume to be, say, like closer to 1,000 meters in distance or in amplitude. Now let's talk about short waves. Say if I wanted to just have a continental traveling of a message, say from Russia to North Pole, I would have to be using short waves, and it's safe to say that these would be around 100 meters in wavelength. And then say if I just wanted to transfer a message from Ontario to Ontario, which is the province I live in, I would just need a short wavelength. So it is safe to assume that the wavelength of my system over here is probably around 1 meter, because I'm just communicating in a local area. In order to convert the electricity into rotational force, I have used a DC motor. And on top of that DC motor, as you can see, I have attached a magnet. Now, why? Well, in order to understand the why, we need to understand the how. How does a DC motor work? First off, north and south poles attract, and north and north poles repel. Applying that concept and the concept of electromagnetic fields, we can have a coil with a positive and negative lead and a magnetic field. And with how this is set up, it could go anti-clockwise. There are a few factors which can make that force bigger. One of them is increasing the current. The other is having this coil thicker. And the third, which I've used, is to increase the magnetic flux. I've increased the magnetic flux by adding a magnet to the outside of the motor. But I would also like to remind you of the left-hand rule. Your middle finger would be the current, your index finger is magnetic field, and your thumb is your force. Meaning that if the force is going in a circular fashion, the electric field will, your electric field will be moving as it is going at a counterclockwise fashion along with your magnetic field. That is why there is the use of a commutator. So as it turns, there is a commutator over here which flips positive and negative every time this whole coil turns 180 degrees. And that explains how motors work and how they're useful in the case of this car. It's the first attempt of me creating a successful engine which actually works, and also the steering system. Let's drive your attention, pun intended, to the front of the car. As you can see right off the bat, that the front wheel's axis or radius, or rather the rod, just to make it very clear, is a lot longer than the rod used in the back. This gives you a better angle to prove my point. And that is because of the equation Fc equals mv squared, which is the equation we learned in our course for centripetal motion. As you can see, if mass is reduced and the radius is increased while the velocity stays constant, the force needed to turn the wheels in a circular fashion would be limited. And that is why the front wheels are smaller and hence less heavier than the back wheels. And that's why the axle is also larger. It uses concepts from circular motion. Working on this project has been by far the most rewarding academic experiences in my academic career. This is because although it is cost ineffective and it takes a lot of time, I believe I've learned problem solving and controlling my emotions when things don't go as planned. But other than that, I have learned how to apply all the knowledge I have in a creative manner, which could hopefully one day serve the community. With all that being said, go project-based learning.